In this lesson, we're going to talk about complex numbers. The figure at the right shows that the function f of x equals x squared plus 1 has no real zeros. So, x squared plus 1 equals 0 has no real number solutions. To remedy this situation, mathematicians in the 17th century extended the definition of the square root of a to include negative real numbers a. First, the number I, which equals square root of negative 1, is defined as the solution of the equation I squared plus 1 equals 0 and is the imaginary unit. Then for any negative real number square root of a, that's going to equal the square root of a times I. The extended system of numbers called a complex numbers consists of all real numbers and sums of real numbers and real number multiples of I. The following are all examples of complex numbers. Negative 6, 5i, square root of 5, negative 7i, 5 over 2i plus 2/3, negative 2 plus 3i, 5 minus 3i, 1/3 plus 4/5 i. Those are all examples. Now, the definition of a complex number, that's any number that can be written in the form a plus bi, where a and b are real numbers. The real number a is the real part, and the real number b is the imaginary part. And a plus bi is the standard form. Now you're probably wondering to yourselves, well, if a plus bi is a complex number, how is negative 6 going to be a complex number? You can rewrite that as negative 6 plus 0i. The same thing with 5i. That can be written as 0 plus 5i. Those would both be in standard form. Now, real number a is a complex number a plus 0i, so all real numbers are also complex numbers. If a equals 0 and b doesn't equal 0, then a plus bi becomes bi and is an imaginary number. For instance, 5i and negative 7i would be considered imaginary numbers. Two complex numbers are equal if and only if their real and imaginary parts are equal. For example, x plus yi equals 2 plus 5i if and only if x will be 2 and y will be 5. Now we can add, subtract, multiply, and divide complex numbers. We're going to start off with addition and subtraction. If a plus bi and c plus di are two complex numbers, then a plus bi plus c plus di will be a plus c, we're going to add their real parts, and b plus di, we're going to add their imaginary parts. The difference would be the same thing, except we're subtracting. Simple enough. Let's move on to example 1. Write the sum or difference in the standard form a plus bi. So what we'll have 7 plus 4 plus a negative 3i plus 5i. That will simplify to 11 plus 2i. Now if you look at b, we'll have 2 minus 8 correction, let's try that again. Let's rewrite this as 2 minus I plus a negative 8 minus 3i. Makes it a little easier to work with. So what we'll have 2 plus a negative 8 plus a negative I minus 3i. Simplifying that, we'll have negative 6 plus a negative 4i, so we go minus 4i. Now, if you look at C, it's not written, both of them are not written in standard form. Let's write them in standard form. To make it easier. And also, I changed the signs here. So I'm having 2 plus 3, which is 5, I plus a negative 9i will be a negative 8i. Now the additive identity for the complex numbers is 0 equals 0 plus 0i. The additive inverse of a plus bi is negative a plus bi, or negative a minus bi, because a plus bi and negative a minus bi will give you 0. Many of the properties of real numbers also hold for complex numbers. These include commutative property for addition and multiplication, associative properties of addition and multiplication, distributive properties of multiplication over addition and subtraction. We'll get into that. The one big thing that we need to remember, though, using these properties and the fact that I squared equals negative 1, complex numbers can be multiplied by treating them as algebraic expressions, just like you FOIL back in algebra class. So let's look at example 2. Write the product in standard form. 2 plus 5 is 10. 2 times a negative I is a negative 2i. 3i times 5 is 15i. 3i times negative 1 is a negative 3i squared. Well, because I squared is negative 1, negative 3 times I squared, this will actually be a positive 3. 10 plus 3 is 13. Negative 2i plus 15i would be 13i. Moving on to part B. 2 times 1 is 2. 2 times 3i is 6i. Negative I times 1 is a negative I. Negative I times 3i would be a negative 3i squared. Again, the negative 3i squared will go to a positive 3. 2 plus 3 is 5. Negative, or 6i minus I would be 5i, and there you have it. Now, we can generalize the numbers in example 2 to do AC minus BD plus AD plus BCI. We can do that. So what we'll have is 10 minus negative 3, which will be 13, and then we'll have negative 2i plus 15i will give us a 13i. That does work. Again, you don't have to remember those letters, just work through the FOILing. Many graphers can perform basic calculations on complex numbers. The figure at the right shows how the operation of example 1 and 2 look on some graphers. Well, if we look at that, you pull up your grapher. Your I value, or how to get I in your calculator, is actually pretty simple. So say we do 7, so do parentheses 7 minus 3. To get I, it's the second button, decimal point, plus 4 plus 5i. And your calculator will return 11 plus 2i. Now, if you wanted to multiply them, 2 plus 3i times 5 minus I, you'll get the same thing here, 13 plus 13i. Now, we compute positive integer powers of complex numbers by treating them as algebraic expressions. Now, moving on to example 3, it says, write the complex number in standard form. Well, really what we're going to have, 1/2 plus square root of 3 over 2i squared really means...
Jordan Lance, please call 6241.
It really means 1/2 times square root of 3 over 2i times 1/2 plus square root of 3 over 2i. So when you multiply these, the first, 1/2 times 1/2 is 1/4. 1/2 times square root of 3 over 2i would be square root of 3 over 4i. Same thing for the I term for FOIL. Plus 3 over 4i squared. Well, from the previous example, you should know that 3/4 I squared is really a negative 3/4 because I squared is negative 1. So 1/4 minus 3/4 would be a negative 1/2. Square root of 3 over 4 plus square root of 3 over 4. Well, that will actually get you 2 square root of 3 over 4. Doing a little simplifying, we'll end up getting negative 1/2 plus square root of 3 over 2i. Now moving on to b, it says to the third power. So because it says to the third power, really what we can do here, we can take the squared times the original variable. So we can actually take our answer from part A, stuff it into part B, and multiply like normal. So we don't have to do as many calculations. So when you multiply this, negative 1/2 times 1/2 is negative 1/4. Negative 1/2 times square root of 3 over 2i would be negative square root of 3 over 4i. And then we'd have the positive for that part. And then we'd get plus 3 over 4i squared. Well, just like before, we should see that 3 over 4i squared will really be a negative 3/4. That term and that term will cancel out. So end up having negative 1/4 minus 3/4 will be negative 1. Now example 3 here, 3b, demonstrates that 1/2 plus the square root of 3 over 2i is a cube root of negative 1 and a solution of x cubed plus 1 equals 0. Later in section 2.5, complex zeros of polynomial functions will be explored more in depth. Now the product of the complex numbers a plus bi and a minus bi is a positive real number. So a plus bi times a minus bi will be a squared minus bi squared. So it'll be a squared plus b squared. We introduced the following definition to describe this positive relationship. The complex conjugate of the complex number z, and z is a plus bi, will be a minus bi. Now the multiplicative identity for the complex numbers is 1, which is 1 plus 0i. The multiplicative inverse or reciprocal of z equals a plus bi. So the z inverse or 1 over z, you'll end up getting a over a squared plus b squared minus b over a squared plus b squared I. We're really not going to worry too much about this here. It's going to be an algebraic operation. That's what I want you to understand. Now, in general, a quotient of two complex numbers written in fraction form can be simplified, justly simplified 1 over z, by multiplying the numerator and denominator of the fraction by the complex conjugate of the denominator. Now, if we look at example 4, it says write the complex number in standard form. Well, the complex conjugate of 3 minus I will be 3 plus I. So when we multiply fractions, we're going to multiply across. 2 times 3 is 6. 2 times I is 2i. 3 times 3 is 9. The plus 3i minus 3i, the minus I squared. So when you simplify, the 3 i's will go away. This will be a positive 1. So really it would be 6 plus 2i over 10. Simplifying this further, we'll have 6 over 10 plus 2 over 10i, which will simplify them to 3 over 5 plus 1 over 5i. Moving on to part B. Again, we're going to multiply by the complex conjugate. 2 plus 3i over 2 plus 3i. Simplifying, we'll have 10 plus 15i plus 2i plus 3i squared.
Mike Phillips, call 6109, please.
Over 4 plus 6i minus 6i plus 9i, sorry, not plus, minus 9i squared. Simplifying this, we should know that this is a negative 3. This will be a plus 9. So we'll have 7 plus 17i on top. The 6 i's will go away, but 4 plus 9 on the bottom. So really, it'll end up being 7 over 13 plus 17 over 13i. Moving on to part C. Again, we're going to multiply by the complex conjugate of having 2i plus I squared on top over 4 minus I squared on the bottom. That'll actually be, this is negative 1, this will be positive 1, so we'll have negative 1 plus 2i over 5. That will simplify to then negative 1/5 plus 2/5 I. Simple enough. Recall that the solutions of the quadratic equation ax squared plus bx plus c equals 0, where a, b, and c are real numbers, and a can't equal 0 are given by the quadratic formula. The radicand, b squared minus 4ac, so the stuff underneath the radical sign, is the discriminant and tells us whether the solutions are real numbers. In particular, if b squared minus 4ac is less than 0, which means it's negative, if the solutions involve the square root of a negative number, and so lead to complex number solutions. In all, there are 3 cases. Well, the discriminant could be positive. Well, there will be 2 distinct real solutions. The discriminant could equal 0, which means there's 1 repeated solution, or it could be less than 0, so there's going to be a complex conjugate pair of solutions. Example 5 should help us out with that. Now it says solve the equation. We can do this one of 2 ways. From section P.5, we learned the quadratic formula. We also learned completing the square. I will use the quadratic formula here. So x will equal the opposite of b plus or minus b squared minus 4 times a times c, all of that over 2a. You should realize by now that our discriminant will be negative. So negative 1 plus or minus. 1 squared is 1. Minus 4 would be a negative 3. All of that over 2. So when you simplify this further and take out the negative 3, you'll have a negative 1 plus or minus the square root of 3i over 2. Finishing this up, x will equal negative 1/2 plus or minus square root of 3 over 2i. So remember, there are 2 solutions there. It would be negative 1/2 plus the square root of 3 over 2i, and negative 1/2 minus the square root of 3 over 2i. Now for part B, instead of using the quadratic formula, I'm going to complete the square. So x squared plus 2x, I'm going to bring the 5 to the other side, make it negative. Half of 2 is 1. So when you factor this, well, x plus 1 squared equals a negative 4. When you take the square root of both sides, the square root of negative 4 is really plus or minus 2i. So x will equal negative 1 plus or minus 2i. Now, if you should have any questions on complex numbers, please do not hesitate to ask me. I will be in here every day before 7:30.